Welcome, and get ready to dive deep into a topic that's quite literally shaping our future: wireless communication in 2030 and beyond. Our goal here is really to unpack what 6G is all about, because, as we'll hear, it's shaping up to be, well, a lot more than just faster phones.
And the Alpert team, they frame 6G as this intelligent foundation. It's not just the next step up, They see it transforming, well, everything, but the digital world and the physical one. It could genuinely spark completely new industries we haven't even thought of yet.
Right, moving beyond just connected things to intelligent infrastructure.
Exactly. Truly cognizant infrastructure.
This deep dive examines the limitations of 5G, identifies the key technological and societal drivers accelerating the shift towards 6G, and articulates the ambitious vision underlying this next-generation network. We'll outline its performance benchmarks, core enabling technologies, and the global standardization roadmap that positions 6G not merely as an incremental upgrade, but as a truly transformative leap beyond just connectivity. So, we just got 5G, right? And it was and still is a massive leap forward in mobile broadband. So why do we need a new generation so quickly? What are the inherent limitations of current generations, particularly 5G, that are putting pressure on us to change?
Is 5G truly enough for the highly anticipated and often extreme demands of 2030 and beyond? According to the Alpert research team's comprehensive report, the answer is a definitive no. And it's due to several key fundamental limitations inherent in current 5G deployments and its underlying architecture.
Okay, what are they?
First, let's talk about congestion and scaling. While 5G offers impressive peak speeds and greater capacity than 4G, it still struggles significantly with congestion in dense urban areas, especially as the number of connected devices and the sheer volume of data traffic continue their exponential increase. The Alpert report cites projections showing data traffic escalating dramatically, potentially reaching 282 exabytes per month by 2027 alone.
282 exabytes. Wow.
Right. This exponential growth presents unsustainable scaling challenges for current 5G architectures. As more and more devices connect, and as emerging use cases become increasingly data-intensive, think high-definition AR/VR streaming or real-time digital twin updates, 5G networks can quickly become bottlenecks. This severely impacts overall user experience and network performance, leading to frustrating slowdowns and service degradation. Critical communications, in real-world scenarios, this ambitious target is often unmet. But a more critical issue for next-generation applications is that jitter, the variability or inconsistency in latency, is not deterministic.
Not deterministic, meaning unpredictable delays.
Exactly. This non-deterministic performance makes 5G fundamentally inadequate for a new wave of emerging, highly sensitive, and time-critical applications. Imagine haptic feedback systems needing instantaneous tactile responses, or remote surgeries where even a slight, unpredictable delay could have severe, life-threatening consequences. Truly autonomous systems, whether self-driving cars or industrial robots, demand not just low latency, but predictable and guaranteed ultra-low latency to ensure safety and precision, which 5G often fails to provide consistently. For example, remote control of automated guided vehicles, AGVs, in dynamic industrial settings requires latencies less than 5 milliseconds to operate safely and efficiently. That's a threshold often beyond 5G's reliable delivery, particularly under load.
Okay, reliability and predictability are key limitations there.
Then there's energy efficiency. This is a particularly significant concern for the long-term sustainability of wireless networks and a major driver for 6G. The Alpert report reveals a stark reality. Despite advancements, 5G base stations, particularly due to their increased densification and reliance on active components for massive MIMO and milling wave, consume significantly more energy than previous generations, up to 3 times more than 4G base stations.
3 times more. That's huge.
It is. This current model is simply unsustainable, both for global climate goals and for the practical economic deployment of infrastructure in remote areas where power access might be limited or costly. And the true insight here, according to Alpert, is that without a fundamental architectural shift, the sheer volume of 6G deployments needed could actually accelerate global carbon emissions.
So it could become an environmental liability. What about coverage? 5G was meant to improve that too.
True, but we still face persistent coverage gaps. Despite its widespread rollout, 5G, particularly in the higher millimeter wave bands, still suffers from sparse and inconsistent coverage due to limited propagation characteristics. Rural areas, deep indoor environments within buildings, subterranean spaces, they often experience significant signal degradation or complete lack of service. This hinders global connectivity goals, creates persistent digital divides, and results in inequitable access to high-speed communication. That's unacceptable for a truly interconnected and inclusive world.
So the promise of ubiquitous connectivity isn't fully realized yet.
Not quite. And finally, a key limitation lies in AI integration. In 5G, artificial intelligence is often used as an overlay. This means it's applied on top of the existing network infrastructure to optimize certain functions like traffic management or resource allocation. It's not natively integrated into the fundamental network architecture, it's more of an external enhancement. This limits its full potential for real-time optimization, truly autonomous network management, and the kind of pervasive, anticipatory intelligence needed to support the complex, dynamic demands of future applications. 6G aims to bake AI directly into the network's DNA, making it an intrinsic part of its operation, not just an add-on.
Okay, so 5G was a huge leap, truly enabling the mobile broadband we enjoy today. But the future demands capabilities that simply weren't built into its core, especially when it comes to true real-time, deterministic performance, pervasive coverage in every nook and cranny, and critically, sustainability. It's a fascinating and urgent challenge that the Alpert report clearly lays out. What are the massive macroeconomic, technological, societal, and industrial trends that are truly pushing wireless innovation forward at an unprecedented pace? It feels like tectonic plates shifting beneath our feet, creating immense pressure for fundamental change and advancement in the wireless domain, almost forcing this next leap.
It's fascinating, actually, how interconnected these forces are, and how their synergy creates an almost unstoppable momentum for a new generation of wireless technology. So, from a macroeconomic perspective, we're witnessing this accelerating and pervasive push for digital transformation, and it's across virtually all sectors of the global economy. Think about healthcare telemedicine, remote diagnostics are becoming standard, or manufacturing, where smart factories are revolutionizing production lines, logistics, aiming for fully autonomous supply chains. Even basic public services are digitizing to enhance citizen engagement and efficiency. The goal here is multifaceted. It's about achieving enhanced operational efficiency, creating entirely new business models that were previously unimaginable, and fostering robust economic growth through digital means. But the Alpert report highlights a fascinating twist here. This isn't just about efficiency anymore. It's becoming a kind of zero-sum game of national competitiveness. Nations or industries lagging in digital infrastructure development could mean falling behind economically and strategically on a global scale.
Right, so it elevates 6G from just a tech upgrade.
Exactly. It becomes a critical national imperative, fundamentally reshaping how governments and industries prioritize investment and policy. This widespread digitalization inherently demands an ultra-reliable, high-speed, and secure communication infrastructure. Without it, these digital transformation initiatives simply can't achieve their full potential.
Makes sense.
Then, moving on to technological advancements, the continuous evolution in cellular wireless networks is, at its core, driven by this relentless, almost insatiable need for higher data rates, exponentially increased network capacity, imperceptibly lower latency, and truly ubiquitous, pervasive connectivity. And this isn't just about making existing services a little bit better or faster. We're moving beyond merely connecting people to connecting everything. Every device imaginable, every sensor in our environment, every vehicle, every piece of critical infrastructure, every physical space. The aim is to create an intelligent environment where data flows freely, intelligently, and instantaneously, forming a vast, distributed digital nervous system. And that ambition requires fundamental breakthroughs and radical architectural shifts. Well, then there are the escalating societal demands. People's expectations for seamless, deeply immersive experiences are rapidly escalating. We're moving beyond static screens to interactive, multisensory digital environments. Whether it's remote healthcare consultations that feel as immediate and personal as being in the same room, or educational platforms offering lifelike simulations. Think transporting students into historical events or complex scientific experiments, or entertainment that completely transports you into virtual or augmented worlds. There's a strong and growing desire for consistent, high-quality user experiences, regardless of your physical location or environmental conditions. Beyond that, there's a growing and critically important emphasis on environmental sustainability. This isn't a secondary concern for 6G, it's a primary driver that consumes significantly less power and dramatically reduced carbon emissions. This is explicitly evident in the alignment of 6G development with the United Nations Sustainable Development Goals, emphasizing energy efficiency as a core design principle from day one. we observe profound industrial transformation. Industries globally are undergoing massive shifts towards advanced automation and highly sophisticated applications, creating an entirely new industrial landscape. We're talking about Industrial Internet of Things, or IoT, deployments with tens of thousands of intercommunicating sensors, complex robotics performing intricate collaborative tasks on assembly lines, and the grand vision of smart cities that manage traffic, public safety, energy grids, and resource allocation in real time, adapting dynamically to changing conditions. These advanced applications absolutely require predictable, deterministic service delivery with truly guaranteed real-time performance. This level of demand pushes the very boundaries of current wireless capabilities, making 5G, for all its advancements, simply insufficient for the truly transformative and mission-critical industrial applications envisioned for the next decade.
That's a powerful summation. It really paints a picture where it's not just about what technology can do, but what society and industry are now demanding it must do, often with critical real-time implications. It's a pull from all sides that's necessitating this massive leap forward, almost forcing a complete rethink of network fundamentals. What are we building all this for? Let's talk about the exciting emerging applications and services that 6G will unlock. This is where the future really comes to life, illustrating the tangible impact and immense potential of these technological advancements.
Absolutely. The vision for 2030 and beyond, as detailed by the Albert research team, is truly transformative. It enables tasks and experiences that are currently unattainable due to existing technological constraints, moving us into a deeply integrated cyber-physical world.
Cyber-physical, so blending digital and real worlds.
One of the most prominent areas is immersive extended reality (XR) and the metaverse. 6G will make virtual reality (VR), augmented reality (AR), and mixed reality (MR) technologies far more immersive, effective, and frankly, indistinguishable from physical reality than they are today. Imagine transforming education with lifelike simulations where students can not only observe but interact with historical events or complex scientific models as if they were physically present. In industries, it will allow workers to overlay real-time data onto physical objects for complex maintenance and repairs, providing a virtually seamless experience that enhances precision and reduces errors.
Like AR glasses showing repair steps directly on the machine.
Exactly. And a powerful example of a 2030 era use case is holographic telepresence, where realistic full-body holograms of people can appear in remote locations, requiring virtually zero latency services and a perfectly consistent user experience, even in dynamic 3D environments.
Holograms, like Star Wars.
Getting closer. This also includes concepts like multi-user XR, such as VR-based online training sessions or massively multiplayer online gaming, all demanding incredibly high-quality immersive material, precise localization, and perfect stream synchronization across multiple users to prevent motion sickness and enhance truly collaborative experiences. In the realm of industrial automation and robotics, 6G will deliver ultra-reliable, low-latency communication with truly predictable, deterministic performance guarantees. This is absolutely critical for driving advanced automation in smart factories, where dense Internet of Things (IoT) deployments will enable real-time monitoring of every component and precise, synchronized robot control. This vision extends to autonomous logistics with automated guided vehicles, AGVs, which, as we mentioned earlier, require latencies less than 5 milliseconds to operate safely and efficiently, orchestrating complex movements of materials and products without human intervention, leading to unprecedented levels of efficiency and safety. For smart cities, 6G will power ubiquitous and pervasive sensor networks that enable real-time monitoring for everything from dynamic traffic flow optimization to granular air quality management across city blocks. For instance, public infrastructure asset management can be vastly improved with continuous, real-time data from sensors embedded in bridges, roads, utilities, allowing for predictive maintenance and more efficient resource allocation, preventing failures before they occur. Smart traffic management will become truly intelligent, adapting to conditions in real time to minimize congestion, reduce emissions, and enhance public safety by dynamically controlling traffic signals and informing autonomous vehicles.
A city that runs itself, almost.
In many ways, yes. Telemedicine and remote surgery are also poised for a revolution. 6G will enable crystal-clear, high-definition video calls for remote diagnostics, continuous real-time patient monitoring from anywhere in the world, and even complex robotic surgery performed by a surgeon located thousands of miles away. These advancements will significantly broaden healthcare access, especially in less accessible or rural regions, by promoting greater reliability, precision, and the ability to bring specialized care directly to the patient, regardless of location.
Remote surgery. That's incredible.
And a truly groundbreaking concept envisioned by the Alpert team is the digital twin of the human body, which could involve over 100 sensors per person, providing continuous, accurate health assessment and enabling timely intervention based on predictive analytics, allowing for truly personalized and preventative medicine.
A digital twin of the human body with over 100 sensors. That's simultaneously revolutionary and, frankly, a little daunting. How does the report envision the acceptance and privacy challenges of such intimate, continuous data collection? It sounds like an incredible leap in personal health, but also raises significant questions for society.
That's an excellent point about the societal implications, and the report absolutely addresses the need for robust ethical frameworks and strong privacy by design principles. These are essential to ensure user trust and acceptance. The Alpert team emphasizes that for such intimate applications to thrive, it's paramount that individuals retain full control over their data. With clear consent mechanisms and transparent data usage policies, this will be a critical area for regulatory development in parallel with technological advancements. It has to be. Moving on, the integration of satellite IoT using non-terrestrial networks, or NTN, will provide truly pervasive global coverage. This means seamlessly integrating terrestrial, aerial, like drones, maritime, and satellite networks into a single, cohesive, multi-dimensional system. This comprehensive coverage will support communication in remote areas, enable rapid disaster monitoring, for example, by deploying swarm drones that can act as backup mobile edge computing (MEC) nodes in affected regions.
Drones as temporary cell towers.
Essentially, yes. And it can even provide reliable, high-speed in-flight connectivity for airplanes, turning them into seamless extensions of the global network.
Finally, connectivity everywhere.
That's the goal. And finally, 6G will be the backbone for intelligent autonomous systems. This spans a wide range of applications, from fully self-driving cars relying on ultra-reliable vehicle-to-everything V2X communication for real-time situational awareness and cooperative maneuvering, to coordinated drone swarms performing complex missions like surveillance, mapping, or search and rescue with unprecedented coordination and autonomy. It also includes highly advanced AI-enabled IoT devices that can self-optimize, make autonomous decisions at the very edge of the network, and even share learned experiences with other devices, leading to a truly intelligent, self-organizing ecosystem of connected things.
It's clear that 6G isn't just an upgrade. It's the foundational layer for a deeply integrated, intelligent, and highly immersive digital physical world. These use cases truly bring to life the immense potential and clearly demonstrate why this next generation is so critical to our future.
Exactly.
With all these technical advancements being forecasted and the societal demands clearly defined, what's the overarching vision for 2030 and beyond? How will society, services, and technology co-evolve to create this future world that 6G is meticulously designed to enable? This is where the Alpert research team paints a compelling picture.
Indeed. The vision for 2030 and beyond, as synthesized by the Alpert research team, involves a profound and transformative synthesis. Communication networks become the central, intelligent bridge to a fully cyber-physical world. This isn't merely an upgrade to our current digital experience. It's a fundamental redefinition of how we interact with technology and with each other.
Okay, paint a picture for us.
At its core, we envision a fully cyber-physical world. This means rapid and comprehensive digitalization extending into literally all domains of our lives and work, with advanced AI-powered automation universally available and deeply integrated. What this translates to is that physical objects, people, and their activities will be intricately and dynamically connected through a vast digital domain of intelligence and data. Every interaction, every environment, every physical entity will have a dynamic, intelligent digital counterpart, continuously enriching and optimizing the physical world around us in real time.
Here's where it gets really interesting. Imagine a world where the lines between physical and digital blur completely and everything is intelligently connected for a profound purpose, not just for raw speed. It's a vision that touches every single aspect of our lives and work, from how we interact with our environment to how industries operate.
This leads directly to an unprecedented level of digital-physical convergence. 6G will enable such tight integration between our physical and digital worlds that it will create mixed physical-virtual environments generating truly near real-life experiences. Imagine seamlessly moving between a physical space, say, a factory floor, and its perfectly synchronized digital twin, interacting with both simultaneously to monitor operations or troubleshoot issues. This convergence will fundamentally transform human technology interaction, making interfaces far more intuitive and immersive, moving beyond screens to sensory experiences. Crucially, it will also reshape human interaction, enabling new forms of telepresence and collaboration that feel almost indistinguishable from physical presence, breaking down geographical barriers in truly meaningful ways. We're moving towards an era of the intelligence of everything. The proliferation of intelligence will be pervasive and ubiquitous, creating highly context-aware smart services for both human and non-human users. This moves us firmly into the intelligence of everything paradigm, where every device, every sensor, every component of the network is imbued with intrinsic intelligence. Communication itself will evolve into that distributed neural network we talked about, capable of fusing information from physical, biological, like the human digital twin, and cyber realms. This involves the pervasive integration of AI and machine learning into every aspect of network management, allowing networks to self-optimize, predict needs, adapt in real time, and even self-heal, far beyond what traditional network management can achieve, creating truly autonomous network operations. And beyond just core communication services, 6G will fundamentally expand into a comprehensive platform offering a much wider range of capabilities. This means that beyond communication services like high-precision sensing, advanced localization, AI inferencing will be exposed as readily accessible application programming interfaces, or APIs, to developers and applications.
So opening up the network's capabilities.
Exactly. This programmable connectivity, coupled with these rich beyond communication services, will effectively create a global innovation platform. Developers will be able to easily tap into advanced network functionalities that were previously deeply embedded and inaccessible, allowing for a rapid proliferation of new applications, services, and entirely new business models that we can't even conceive of today.
A platform for innovation. And that brings us perfectly to how the very architecture of these networks is evolving. Let's now peel back the layers and understand how the architecture of communication is fundamentally evolving, moving beyond incremental upgrades to truly paradigm-shifting designs. It feels like we're always building on the last generation, but sometimes it's a complete paradigm shift, right? Fundamentally redefining how networks are constructed.
Absolutely. And if we connect this to the bigger picture, the fundamental shift for 6G is from traditional connectivity-focused networks, where the primary goal was simply to transmit data to intelligence-native systems. This is a profound architectural evolution. We're moving beyond merely transmitting data to enabling a truly intelligent, adaptive, and self-optimizing ecosystem.
But you mentioned the biggest shift is towards intelligence native. What does that really mean architecturally?
Right. That's the most profound and transformative shift, as highlighted by the Alpert research team. This intelligence-native architecture for 6G, it's far more than just AI on the network. 6G aims to deeply embed artificial intelligence at every single network layer, from the very physical air interface where signals are transmitted right up to the high-level application services.
Every layer.
Every layer. This means moving beyond using AI as a mere overlay where it optimizes existing functions to making it a native, intrinsic, and self-organizing part of the network's capabilities. We're talking about a network that behaves like a vast distributed neural network, intelligently fusing physical, biological, and cyber worlds in real time. The very radio access network, or RAN in 6G, is envisioned to operate as a message-oriented middleware. It will utilize a publish-subscribe model, or pub-sub.
Pub-sub, like a software system.
Exactly like that. To use an analogy, imagine the 6G RAN not as a rigid one-to-one phone call system, but as a dynamic, intelligent information marketplace. Instead of every device constantly asking the network for updates, devices subscribe to specific types of data they need, like a self-driving car subscribing to real-time traffic obstacle data, or a smart factory robot subscribing to sensor readings. The network publishes this data, and only the subscribed devices receive it. This makes the entire system incredibly efficient, reactive, and agile, almost like a neural network for information flow.
Okay, that's a powerful analogy.
This asynchronous, message-based nature enables truly reactive tasks and provides a clear audit capability for how AI, particularly large language models, are used within the system. The AI Interconnect Framework, as it's called in the report, will be responsible for selecting appropriate LLMs for specific tasks, crafting strategies, and ensuring seamless communication between these advanced AI models and various network components, essentially turning the network into a vast, intelligent computational fabric.
That's a profound shift. It really does sound like AI isn't just a feature you turn on or off. It's becoming the nervous system of the network, deeply integrated and driving its core functions. That really reframed how we should think about future connectivity. To realize that incredibly ambitious vision we just discussed, this fully cyber-physical world, what are the quantifiable connectivity needs? How much bandwidth, how little latency, how much connection density, and how much reliability do we really need to make this 2030 era a vibrant reality? These aren't just abstract numbers. They are the fundamental, often extreme targets that will dictate network design and engineering.
Right. What are the specific, often audacious performance targets required to enable this future cyber-physical world? The demands, as outlined by the Alpert research team, are truly staggering. They represent orders of magnitude improvement over current 5G capabilities.
Okay, let's hear the numbers. Bandwidth first.
Let's start with bandwidth. User experience data rates are projected to consistently reach multi-gigabit level speeds, meaning you'll seamlessly get multi-gigabit performance wherever you are, enabling instant access to vast amounts of data. However, peak data rates are targeting an astonishing 1 to 10 terabits per second.
10 terabits.
Again, that's up to 100 times the peak data rate of 5G. This immense demand is fundamentally driven by the next generation of multimedia services, fully immersive XR, ultra-high-definition holographic telepresence, seamless streaming, and synchronization of incredibly complex digital twin data in real time. The area traffic capacity, how much data can be supported per unit of area, is expected to exceed 1 gigabit per square meter. Some advanced projects are even targeting 1 to 10 gigabits per cubic meter for 3D deployments, reflecting that need for pervasive high-capacity connectivity throughout three-dimensional spaces like multi-story buildings or dense industrial complexes.
Okay. Massive bandwidth. What about latency? You mentioned microseconds earlier.
Exactly. The ultimate target is sub-millisecond latency, aiming for as low as 100 microseconds for critical applications. To truly grasp this, consider the implications for remote surgery. A surgeon operating thousands of miles away with virtually no discernible delay, allowing for tactile feedback and real-time precision. This also enables the tactile internet, where sensory feedback is transmitted instantaneously, or highly precise industrial automation and control systems where robots react with near-zero delay.
Tactile internet, feeling things remotely.
Essentially, yes. For example, remote control of those AGVs in a factory setting requires less than 5 milliseconds of latency to ensure precise, real-time control and avoid collisions. Even for widely adopted applications like cloud gaming, a good user experience demands end-to-end latency below 120 milliseconds. 6G will comfortably surpass that, moving towards truly immersive and responsive gaming. The leap from 1 millisecond to 100 microseconds might sound small, but it's the difference between a slight perceptible delay and a truly instantaneous interaction for human-machine interfaces.
Instantaneous. Got it. Density.
Yeah.
Supporting all those devices.
When it comes to density, the connection density is projected to increase dramatically by 10 to 100 times compared to 5G. This means the networks must support potentially hundreds of devices per cubic meter. This capability is absolutely essential for enabling massive machine-to-machine communication in sprawling IoT deployments. Think smart cities densely packed with environmental sensors, security cameras, intelligent traffic management systems, or hyper-automated smart factories where countless robotic elements and sensors need to communicate constantly and reliably without interference, all vying for network resources.
Hundreds per cubic meter. That's crowded.
Extremely. Finally, reliability is paramount, especially for mission-critical communications. Ultra-reliability is a core requirement, with targets as high as an astounding 99.9999% success probability.
6 nines.
6 nines reliability. For deterministic end-to-end communication services within a given time interval, this level of reliability is crucial for applications like smart factory automation, where a single lost packet or a momentary communication failure could lead to production halts, safety issues, or catastrophic system errors with potentially significant economic impact. Similarly, for critical communications and emergency services, lives can depend on every message reaching its destination flawlessly. Packet loss rates are targeted to be extremely low, often less than 0.01%, ensuring that crucial data always reaches its destination without compromise.
So it's not just a little more of everything, it's orders of magnitude more, with an almost obsessive emphasis on perfection, particularly for specific mission-critical use cases. It sounds like a completely different league of connectivity pushing the boundaries of engineering. That's truly fascinating. So if these are the incredible, almost dizzying goals we're aiming for, how exactly are we going to achieve them? Let's delve into the core enabling technologies that will make 6G a reality. We're talking about things like Terahertz Communication, Reconfigurable Intelligent Surfaces, AI-native networking, Non-Terrestrial Networks, and deep edge cloud integration. This is truly where the technical magic happens, where the theoretical becomes the practical.
This is indeed where the rubber meets the road, outlining the comprehensive and often groundbreaking technological toolkit that will underpin 6G, enabling those extreme performance targets.
Okay, let's start with terahertz. What exactly is that?
First, terahertz communication explanation. Terahertz communication utilizes extremely high frequencies, specifically in the range between 0.1 terahertz, that's 100 gigahertz, and 10 terahertz. This range offers ultra-wide bandwidths, which are absolutely crucial for enabling the astonishing Tbps-level data rates that 6G targets. To truly understand terahertz communication, consider the shift from gigahertz frequencies, which 5G primarily uses, to terahertz frequencies as a transition similar to moving from traditional copper wires to high-capacity fiber optics. It's about unlocking vastly more capacity by using a much higher frequency spectrum, allowing us to encode much more data simultaneously.
Like fiber optics, but through the air. Sounds amazing, but what are the catches?
There are significant challenges. Because these waves are so incredibly small and high frequency, they act almost like tiny, delicate laser beams. They suffer from severe propagation loss over distance, meaning their signal strength diminishes very rapidly. They are also highly susceptible to atmospheric attenuation, particularly from water vapor and oxygen molecules in the air. Imagine trying to shine a laser through dense fog. The signal quickly dissipates.
So they don't travel far easily.
Exactly. This means their effective communication range on the ground is severely limited to very short distances, primarily for line-of-sight LOS applications. Conversely, in the vacuum of space, they can enable very long distances between satellites where there's no atmospheric interference. Furthermore, current hardware struggles to produce high-power Thertz transmitters and sensitive, low-noise Thertz receivers. These are essential for stable and reliable signal generation and reception at these ultra-high frequencies.
Okay, big challenges. How do we solve them?
Several innovative solutions are being developed. Ultra-directional antennas and high-gain beamforming are crucial to precisely direct and steer Thertz beams, acting like powerful spotlights to concentrate the signal and compensate for rapid path loss. Multi-hop relaying can extend the communication range by retransmitting signals over shorter segments. Tunable intelligent surfaces, which we'll discuss next, are also vital for intelligently reconfiguring the wireless environment to guide signals around obstacles. And photonic integration, using light-based technologies to reduce coupling losses and enable multi-antenna systems on a chip, is a promising solution for improving both transmitter power and overall system efficiency, making Thertz devices more practical and scalable.
Okay, so highly focused beams and smart surfaces. Let's talk about those surfaces. Reconfigurable Intelligent Surfaces, or RIS.
Next, we have Reconfigurable Intelligent Surfaces, RIS. Explanation. RIS are truly innovative and somewhat counterintuitive components. They are essentially small, passive, and modular devices. Think of them like smart, programmable mirrors for radio waves that can dynamically reconfigure the wireless propagation environment. They achieve this by intelligently altering the phase shifts of the radio signals they receive and reflect. This unique capability enables precise, intelligent steering of wireless links, effectively create smart walls or smart windows that can improve network robustness, extend coverage into dead zones, and enhance overall reconfigurability.
Smart mirrors for radio waves. Interesting. What are the benefits?
The advantages of RIS are compelling and align strongly with 6G's goals. They are easy to deploy in various environments due to their small form factor and modularity. They offer highly sustainable operation due to their negligible power consumption, making them a key building block for green communication systems.
Low power consumption is huge.
Absolutely. By actively shaping the radio environment, RIS increases overall system efficiency and dramatically improves spectrum utilization. Unlike 5G, where beamforming is primarily active and controlled by energy-intensive base stations, 6G will leverage RIS to shift beamforming towards a more distributed, passive-active model with AI-based adaptation, offloading some of the energy-hungry tasks.
Sounds great. Any challenges with RIS?
Developing RIS components that can efficiently operate at the incredibly high Thertz frequencies poses specific challenges. It requires novel tuning mechanisms and advanced materials, including cutting-edge CMOS transistors, high-speed Schottky diodes, innovative graphene-based elements, and precision MEMS for dynamic control. Still work to be done there.
Okay. Now let's revisit AI native networking. You said it's core to 6G?
Yes, a core and transformative vision for 6G is AI native networking. Explanation. This concept goes far beyond simply using AI as an overlay tool. It involves embedding AI at every single layer of the network stack, from the physical air interface right up to the application services. The goal is to create a truly self-optimizing, self-healing network that can anticipate and respond to user needs and dynamic network conditions in real time, operating with minimal human intervention.
How does it function differently?
Functionality. AI native networks facilitate pervasive AI-centric operations across the control plane, user plane, and even higher-level application elements. Large language models, LLMs, and generalized pre-trained transformers, GPTs, will be central to this intelligence. They will handle complex tasks like understanding nuanced user intent, strategizing optimal network configurations, and executing intricate commands for highly autonomous network management. This includes sophisticated traffic prediction, real-time anomaly detection, and even generating hardware description language, HDL, code for wireless systems to boost design productivity. The AI Interconnect framework detailed in the output report will provide crucial messaging and brokering capabilities for these LLMs across different network planes, allowing them to collaborate and share insights.
Give us some practical examples.
Examples. Practically, AI will enable real-time network automation, dynamic and predictive traffic management, seamless handover optimization between cells without drops, and the creation of self-healing networks that automatically detect and repair errors, often before users even perceive an issue. This also extends to optimizing power consumption across network layers for enhanced sustainability.
Okay, AI is truly embedded. What about connecting the unconnected, NTNs?
Fourth, we have non-terrestrial networks, NTNs. Explanation. NTNs, which crucially include constellations of low Earth orbit, LEO, and geosynchronous Earth orbit, GEO satellites, are absolutely critical for complementing terrestrial networks and providing pervasive, truly global coverage. This extends connectivity to previously unconnected regions like polar areas, remote oceans, vast land masses where terrestrial infrastructure is impractical. They enable ubiquitous connectivity by seamlessly integrating terrestrial, aerial drones, high-altitude platforms, maritime, and satellite networks into a single, cohesive, multi-dimensional system.
How do these satellite networks work?
Architecture. NTNs can employ different payload types. Transparent payloads act essentially as analog repeaters, simply amplifying and relaying signals between the ground gateway and the user equipment, like a mirror in the sky. More advanced regenerative payloads actually have full GNODEs on board the satellite. These GMBs can process signals, perform routing, and crucially enable inter-satellite links. These are mandatory for achieving truly global coverage and efficient routing across vast satellite constellations without constantly bouncing signals to ground stations.
Sounds complex. What are the big hurdles?
Challenges. NTNs introduce unique and complex challenges. High latency is a significant concern, especially for GEO satellites due to long propagation delays. LEO satellites, while closer, introduce significant and rapidly changing Doppler shifts due to their extremely high relative speeds, around 7.56 kilometers for a 600-kilometer LEO.
Doppler shifts, like ambulance sirens changing pitch.
Exactly, but for radio waves. This rapid movement also leads to complex mobility management issues, like frequent and challenging handovers between rapidly moving satellite beams as a device travels.
So how do we handle that?
Solutions. Innovations are vital. These include advanced timing, advanced TA refinement to compensate for signal travel time, enhanced two-step random access channel (RACH) procedures to mitigate long delays during initial connection setup, and sophisticated handover mechanisms like those triggered by precise location-based information, leveraging the deterministic movement of satellites and accurate ephemeris data. Pre-provisioning satellite orbital parameters to user equipment is also key.
Okay, lots of smart engineering needed. Lastly, edge cloud integration.
Lastly, edge cloud integration is critical to realize the distributed intelligence of 6G. Explanation. 6G will rely on a flexible and dynamic computing continuum, seamlessly integrating computational capabilities from local edge computing clusters located very close to the user to centralized cloud resources. Edge computing clusters will handle real-time, latency-sensitive AI workloads like complex AR/VR frame synthesis needing immediate processing, or critical industrial automation tasks where instantaneous decision-making is paramount. This decentralizes data processing, minimizing round-trip time and improving responsiveness. Cloud resources, on the other hand, will manage larger-scale data processing, extensive AI model training, and less latency-sensitive tasks.
What's the synergy between edge and cloud?
Synergy. This deep integration supports highly user-centric approaches, allowing for dynamic scripting of new AI model training via edge-federated learning. In this paradigm, models are trained locally on devices at the edge, and only aggregated insights or model updates are shared with the cloud, preserving privacy and significantly reducing backhaul traffic. This creates a powerful distributed learning system.
Sounds efficient. Any challenges there?
Challenges. Implementing this seamless continuum brings its own set of challenges. Managing the immense communication demands between edge and cloud nodes, addressing the significant computational intensity required at the edge for complex AI tasks with limited resources, and solving complex data storage concerns in decentralized edge environments while ensuring data consistency and security.
That's a lot to take in. It's clear that the future of wireless is a symphony of complex, interconnected technologies working together seamlessly, each solving specific monumental challenges to achieve this hyper-connected, intelligent vision. It's an incredibly intricate puzzle. Beyond the individual technologies we've just explored, where are we seeing the most exciting intersections and profound convergences? How do fields like AI, quantum technology, the automotive sector, robotics, and space communications intertwine with 6G to create something truly greater than the sum of its parts? This is where the truly transformative potential of 6G becomes apparent.
This is indeed where the transformative potential truly emerges. As 6G acts as a critical and intelligent bridge between disparate domains, forging a cohesive, self-optimizing ecosystem.
Let's start with AI again. How does it drive convergence?
AI and machine learning, AML, are not just enabling technologies for 6G. They are absolutely central to its cross-domain convergence, fundamentally redefining how networks operate and interact with the world. We're seeing deep integration, far beyond mere optimization, AI-driven automation. AML will enable real-time network performance monitoring, shifting from reactive troubleshooting to predictive maintenance to prevent failures before they occur. It will facilitate dynamic resource allocation based on anticipated demand and sophisticated self-healing networks that automatically detect and repair errors without human intervention. AI algorithms will also be crucial for identifying and addressing evolving security vulnerabilities in real time, dramatically improving network protection and mitigating complex cyber attacks. Essentially, AI-based control loops will continuously monitor network performance, user behavior, and environmental factors to make real-time adjustments for optimal operation, guided by high-level policies.
So AI is the conductor of this orchestra.
In many ways, yes, and LLMs and GPTs. Large language models and generalized pre-trained transformers, as identified in the Alpert report, will be integrated directly into 6G systems. They will be tasked with understanding complex user or network operator intent, strategizing optimal responses, and executing intricate commands across diverse network functions. This redefines network functionalities and interactions, even extending to generating hardware description language, HEL code for wireless systems, significantly boosting productivity in design and development.
And it helps with sustainability, too.
Sustainability, absolutely. AI will significantly contribute to sustainable networks by optimizing power consumption across all network layers, from the core to the edge, and managing energy resources more optimally. The Alpert report cites studies showing that AI has a positive effect on 79% of the UN's sustainability goals, acting as a powerful catalyst for developing more environmentally friendly and human-centric technologies.
Okay. AI is central. What about quantum technology? That sounds very futuristic.
Next is the exciting frontier of quantum technology, which holds immense promise for security and computation within 6G. Impact. Quantum-based methods, including quantum communication and computing, offer promises of much higher processing capability for complex optimization problems, lightweight solutions for certain cryptographic functions, and absolute randomness in cryptographic key generation, far beyond what classical computing can achieve.
How does it help with security specifically?
Security. Quantum cryptography, encompassing both pre-quantum classical algorithms resistant to quantum attacks and post-quantum methods, is seen as a robust solution for ensuring data security and privacy in a future 6G world. Quantum key distribution, QKD systems, which generate cryptographic keys based on the fundamental uncertainty of quantum states, are expected to be applied in various 6G networks, including satellite, optical fiber, and even oceanic networks. They provide unconditional security guarantees that are theoretically unbreakable by classical computers, offering a new gold standard for data protection.
Unbreakable keys.
Yeah.
Very interesting. What about cars? Automotive?
The automotive sector, particularly connected vehicles, will be fundamentally transformed by 6G. 6G-based V2X, vehicle to everything, communication is foundational for developing fully self-driving cars, intelligent traffic management systems, and cooperative driving. These applications demand ultra-reliable, ultra-low latency links for real-time sensor data sharing between vehicles, infrastructure, pedestrians, and the cloud, enabling cooperative perception and collision avoidance. The projected data demand for connected vehicles is an immense 0.15 terabits per second, underscoring the need for 6G's extreme capacity.
Huge demand.
And robotics. In robotics, 6G will empower advanced applications far beyond current capabilities, especially in collaborative industrial automation, precision manufacturing, and highly sensitive remote surgery, demanding that ultra-low latency and ultra-high reliability for precise control and haptic feedback. The integration of blockchain technology can further enhance robot avatars within 6G networks, providing decentralized identity management and enabling smart contracts for robot as a service, RAIS deployments, ensuring secure, autonomous, and auditable service agreements between machines.
Blockchain for robots.
Okay.
And space communications. We touched on NTNs.
Space communications through non-terrestrial networks, NTNs, and satellite IoT are central to 6G's vision of truly global, seamless coverage. This creates an integrated space, air, ground, sea network, a multi-layered fabric of connectivity, dynamic topology. Satellite networks, particularly LEO constellations, have highly dynamic topologies due to their rapid movement, posing unique challenges for routing and mobility management that 6G networks must intelligently address. Swarm drones. These will become indispensable for flexible and adaptive communication solutions, acting as rapidly deployable backup MEC nodes in disaster scenarios and optimizing computation offloading and caching services by dynamically adjusting their positions based on real-time network needs. Inter-satellite links. Regenerative payloads on satellites are mandatory for establishing efficient inter-satellite links. These links are crucial for extending global coverage and reducing reliance on ground stations, allowing data to be routed entirely through space.
Connecting everything everywhere. Finally, digital twins.
Finally, digital twin technology will be immensely supported and supercharged by 6G. 6G will enable sophisticated digital twins, which are real-time, highly accurate virtual models of physical entities. This can range from industrial assets in a smart factory, allowing for real-time monitoring, predictive maintenance, and simulation of operations, all the way to that digital twin of the human body, involving potentially over 100 sensors per person, continuously mapping physical and biological data into a precise virtual replica, enhancing health assessment, predictive diagnostics, and enabling highly personalized interventions. This convergence means the network itself becomes a living, intelligent mirror of the physical world.
It's like all these separate technological rivers are converging into one massive, intelligent ocean of connectivity, where the boundaries between physical and digital and between different fields of technology are blurring completely.
Well, the evolutionary path towards 6G involves a continued yet significantly accelerated evolution of 5G advanced functionalities. This happens specifically through the 3GPP releases, which define the standards. Now, maybe it's helpful to take a quick look back at how we got here, tracing the remarkable evolution of wireless communication over the past few decades, and then projecting forward towards 6G and beyond to understand the truly remarkable leap in capabilities we're about to witness. This historical perspective helps frame the scale of 6G's ambition.
Good idea. A little history lesson.
Our historical view from 1G to 5G illustrates a consistent and accelerating drive for more advanced, faster, and more capable communication. 1G, introduced in the early 1980s, was all about rudimentary analog voice communication. It brought mobile phones to the masses, but call quality was often poor, security minimal, calls easily intercepted.
The brick phones.
Those were the days. 2G, arriving in the early 1990s, marked the pivotal shift to digital voice communication and introduced essential services like SMS text messaging, a significant step in both security and network capacity. 3G, launched in the early 2000s, brought the mobile internet to our phones, enabling basic data services, rudimentary web browsing, multimedia messaging, albeit at relatively slow speeds that often tested our patience.
I remember waiting for pages to load.
We all do. 4G, specifically LTE, which became widely prevalent in the 2010s, delivered true mobile broadband. Speeds typically up to 1 gigabit per second in ideal conditions, latency reduced significantly to around 50 milliseconds. This generation truly enabled widespread modal video streaming, robust online gaming, and a host of new data-intensive online applications that transform daily life.
4G really changed things.
It did. And now, 5G, standardized as IMT 2020, has been rolling out since roughly 2020. It focuses on three primary scenarios: enhanced mobile broadband, EMBB, for high data rates; massive machine-type communications, MMTC, for connecting vast numbers of IoT devices; and ultra-reliable, low-latency communications, URLLC, for critical real-time applications. Its peak data rate is specified at an impressive 20 gigabits per second, with a user experience data rate targeted at 0.1 GBps, latency targeted less than 10 milliseconds, supports mobility up to 500 kilometers. Connection density jumped to 1 million devices per square kilometer, area traffic capacity set at 10 millipees per square meter. Crucially, 5G aimed for 3x spectrum efficiency and a remarkable 100x energy efficiency compared to 4G, showing that growing emphasis on sustainability. Key technologies enabling 5G included millimeter wave frequencies, massive MIMO antenna systems, and ultra-dense networks, UDN, with numerous small cells.
So 5G already brought massive improvements across the board.
Indeed.
Let's start with the official timelines. Standardization bodies.
Let's first look at the official standardization timelines, which provide a formal roadmap for the industry. ITU are IMT 2030. The International Telecommunication Union Radio Communication Sector, ITU-R, began its formal framework process for IMT 2030, which broadly defines 6G back in 2019. The critical phase for establishing detailed requirements and evaluation criteria for 6G technologies is set to continue until 2026. Following that, the period from 2026 to 2028 is designated for rigorous evaluation of proposed technologies and building consensus among global stakeholders. Final approval for the comprehensive 6G framework, setting the stage for global harmonization, is anticipated around 2030.
So ITU sets the big picture by 2030. What about 3GPP, the Mobile Standards Group?
3GPP. They officially committed to 6G specifications in late 2023. Currently, Release 19 is underway and expected to be completed by mid-2025. This release already includes preliminary studies for 6G, delving into areas such as integrated sensing and communication, ICs, and new frequency range 3 FR3 channel modeling. So the seeds of 6G are already being planted within current 5G advanced work. Release 20, which will serve as that crucial bridge between 5G advanced and initial 6G, is slated to start in the second half of 2025. It will focus on further enhancements to 5G advanced while simultaneously initiating a series of dedicated 6G studies covering use cases, service requirements, deployment scenarios, and core technology components. The first official 6G release specification, known as Release 21, is expected to be available in the 2029-2030 timeframe, marking the official blueprint for initial commercial deployment.
So Release 21 around 2029-2030. When do we expect actual commercial service?
Commercial deployment. Based on these ambitious and globally coordinated standardization timelines and ongoing industry developments, the general expectation in the wireless industry is that the first commercial deployments of 6G will commence around 2030, with a more widespread rollout accelerating throughout the early 2030s.
It's truly an exhilarating prospect, but also raises the practical question: how far along are we on this journey? That vision is absolutely incredible, but it leads to a very practical question for our listeners who are thinking about strategic planning and investment. How far along are these groundbreaking technologies right now? What's still experimental, what's emerging, and what's closer to being deployment ready? Can you give us some illustrative timelines and discuss the implications so we can understand the strategic path forward?
This is indeed critical for strategic planning, resource allocation, and understanding investment opportunities. The journey to 6G involves distinct and globally coordinated phases of development and standardization, and different technologies are indeed at varying stages of maturity, moving at different paces.
Okay, 2030 is the target year. Now, how mature are the individual technologies we discussed?
Right. Regarding technology maturity and traction, we see a spectrum of readiness across the various enabling technologies. Experimental emerging technologies, still in R&D to pre-standardization. Terahertz Communication. This technology is largely in the R&D phase and early pre-standardization efforts. The ITU has identified the T-Hertz band, 100 gigahertz, 10 terahertz, as a key enabler, and IEEE 802.15.3D outlines its use. However, significant engineering challenges remain, particularly in mass fabrication of high-power transmitters and sensitive receivers.
So kilohertz is still mostly lab work.
Largely, yes. AI native networks. This is an area of intense active R&D and early proof-of-concept PUC-ONI implementations. Companies like Samsung are already demonstrating AI RAN technologies and showing promising POC results. The goal is to transition from AI as an overlay to a native, self-optimizing component. The deeper integration of LLMs and GPTs is a particularly novel and highly active area of research. Reconfigurable Intelligent Surfaces, RAIS, also primarily in R&D, attracting significant academic interest and investigation under standards like IEE 802.11bf. While highly promising for energy efficiency and flexible beamforming, developing RAIS opponents for 2 Hz frequencies requires novel tuning mechanisms and advanced materials still under development. Quantum cryptography. This remains an emerging area with much research still underway. However, quantum key distribution (QKD) systems are expected to see limited, high-security deployments in various 6G networks, like satellite and optical networks, as a cutting-edge layer of data protection.
Okay, so Terahertz, native AI, RIS, quantum are still emerging. What's closer to ready?
Deployment-ready early adoption technologies, building on 5G advanced progress, massive MIMO. This technology is already a key solution for beyond 5G, E5G, and 6G. It's seeing widespread early adoption in 5G, and continuous enhancements are ongoing, such as cell-free massive MIMO, providing higher spectral efficiency and improved coverage. Non-Terrestrial Networks, NTNs, recognized as crucial and were already part of 5G Release 17. 3GPP Technical Report 38.821 provides detailed scenarios and mobility solutions. Enhancements for NTN mobility management and integration are actively ongoing through 5G Advanced, making them increasingly viable.
So NTNs are quite mature already.
Relatively speaking, yes, the foundational work is solid. Integrated Sensing and Communication, ISAC, identified as a foundational capability for 6G. ETSI has already released its first report on ISAC, outlining practical use cases, signaling its readiness for integration into future standards. Edge cloud integration. The seamless integration of edge computing with cloud resources is already being widely implemented and refined in current 5G advanced deployments to support real-time AI workloads, bringing processing closer to the data source.
Okay, so a mix of emerging and maturing tech. What are the broader implications of all this for the industry?
The implications are profound, especially for you, our professional listener. The Alpert report highlights that the anticipated significant financial investments required for 6G deployment are expected to be substantially higher than for previous generations. These costs are primarily driven by the advanced densification required, the development of new, complex hardware for Terahertz and RAS, and the demand for enhanced performance across all network segments.
Higher costs. What does that mean for businesses?
For industry players, this means not just navigating massive capital expenditure, CapEx, but fundamentally rethinking return on investment ROI models, exploring new public-private partnerships, and potentially even driving consolidation in certain market segments as smaller players struggle with the investment burden. However, despite the high initial costs, there are strong prospects for 6G implementation in pervasive services, indicating a clear and compelling business case based on new revenue streams and efficiencies.
So high cost, but high potential return. What about regulations?
Furthermore, the regulatory landscape is bound to evolve dramatically. The sheer pervasiveness of 6G, with its deep AI integration, sensitive data streams, and global reach through NTNs, will necessitate entirely new policy frameworks around privacy, data sovereignty, ethical AI deployment, national security. Your engagement with policymakers won't just be helpful, it will be absolutely critical in shaping the rules and ethical guidelines of this new hyper-connected world.
So what this all means is that while some parts of the 6G puzzle are already here, building on lessons learned and advancements from 5G, many of the truly revolutionary aspects are still being forged in research and development labs around the world. But there is a clear, globally coordinated path to commercialization and widespread deployment by 2030, a roadmap that requires significant strategic foresight and investment from all of us in the industry.
Exactly. In summary, our deep dive into the Alpert research team's comprehensive report reveals a clear, ambitious, and fundamentally transformative trajectory for wireless communication toward 2030 and beyond. This isn't just a simple generational upgrade, it's a fundamental reimagining of our entire connected world.
Let's recap the key takeaways then.
Here are the core key takeaways from our extensive discussion. Driving forces. The evolution towards 6G is propelled by that insatiable demand for higher data rates, lower latency, and ubiquitous connectivity. Fueled by societal shifts towards immersive experiences and industrial automation, all underscored by the critical imperative for environmental sustainability. Architectural shift. We're witnessing a fundamental paradigm shift from connectivity-centric to truly intelligence-native networks. AI deeply embedded at every layer, fundamentally reshaping network design and making it autonomous. Necessity for 6G. Current 5G capabilities, despite their advancements, are insufficient for the extreme performance, pervasive coverage, and inherent intelligence requirements of the 2030 era. Limitations in congestion, guaranteed latency, energy efficiency, coverage, and native AI integration make 6G necessary. Transformative use cases. 6G unlocks applications like immersive XR, holographic telepresence, advanced industrial automation, smart cities, and seamless space-air-ground-sea integration, creating a fully cyber-physical world.
Huge potential there.
Performance leaps. Expect unprecedented advancements, bandwidth up to TBps, latency down to microseconds, massive connection density, and extraordinary energy efficiency improvements over 5G, enabling technologies. Terahertz Communication, Reconfigurable Intelligent Surfaces, AR-native networking, non-terrestrial networks, and deep edge cloud integration are the core technological pillars making this possible. Cross-domain convergence. The future network is deeply intertwined with AI, quantum technologies, automotive, robotics, and space, forming a cohesive intelligent ecosystem, an intelligent physical world. Roadmap ahead. While many technologies are still in R&D, a clear standardization roadmap, ITUR IMT 2030, 3GPP release 20 and 21 is in place, with commercial deployments expected around 2030. This implies significant investment in evolving regulations. As we look toward 2030 and beyond, it becomes increasingly clear that 6G is not simply the next chapter in wireless evolution. It represents a foundational shift in how we connect, compute, and interact with the world around us. Rather than serving as a marginal upgrade to existing systems, 6G is envisioned as an intelligent and adaptive infrastructure layer for a fully cyber-physical society, where artificial intelligence, pervasive sensing, and real-time responsiveness are seamlessly embedded across all levels of our digital and physical environments.
We've reviewed the presentation topic, The Future of Wireless Communication for 2030 and Beyond, prepared by Alpert Research Team.
The next presentation will cover specific topics addressed at the presentation, technical aspects, and other related issues and aspects.